Hi there, nice to have you back. In a previous video, we looked at the concept of a shortest path problem, which is a special case of the transshipment problem in which you're basically moving something, but that something is you, right? You're moving yourself or shipping yourself through a network from point A to point B, and you want to do that at minimum, let's say in quotes, cost, where cost could be something like time or mileage, and that was the shortest path problem. Now today I want to show you that this concept of the shortest path problem can be applied to another type of application that may not at first look like it's a shortest path problem, but indeed it is. And this is the concept of equipment replacement. So imagine a company, for example, like Hertz, right? They have a fleet of vehicles that they rent out. Of course, every now and then they have to replace some of those cars. And then there is a trade-off there to be thought of. On one hand, if we replace these cars too often, we're going to lose a lot of money, right, because of the initial depreciation. That's the bad thing of replacing them often, but on the positive side, replacing them often means we have always brand new or close to new cars, which makes the customers happy. At the other end of the spectrum, we would have let's keep these cars on the fleet for a very long time. That has the advantage of, well, you're not spending so much time buying new cars, but there are two disadvantages. One of them is the fact that the older a car gets, the more likely it is, or more frequently actually, it will require maintenance, which costs money. And secondly, your customers wouldn't be very happy to be driving around in old cars. So there are pros and cons to, replacing more versus less frequently. And what you really would like to do is to come up with an ideal replacement strategy, right? So how often and exactly when should I change this equipment? In the case of Hertz, it's the car. You can think of other examples like this. For example, there are companies that rent out heavy construction machines like backhoe loaders, cranes, and things like that to construction companies that don't want to own their own equipment. These guys face the same problem. How often should I replace my equipment? You can think of a large company that gives computers to employees. Every now and then they have to be replaced. Even when you're driving around, you might have seen these cones or signage at construction sites, and they typically have a company name written on them. So imagine that's a company whose business is, I own a bunch of signage and cones for construction areas. I rent those out to companies that are building something on the road. Every now and then one of those gets damaged, right? Same general idea. How often should I replace my equipment? Great, so this is the problem we're trying to tackle, and as I said before, it can be seen as basically a trip from point A to point B. But in this case, it's a trip in time. So let's take a look at this picture here. Or actually, first let's read a story to put us into context. Consider one less obvious but still useful application of the shortest path problem, which is the equipment replacement. Suppose it costs $10 to buy a new car, right? And the resale values and operating costs of a used car are as follows. So let's say I bought the car new today. I spent $10K. If I want to keep it for 1 year, during that year I will spend $300 in maintenance. And at the end of the year, if I sell the car, I get back $7,000. If I keep the car for 2 years instead of 1, during the entirety of the 2 years, I will spend $500 maintaining it. Okay, so this $300 just for the first year. and the 2-year maintenance is not the sum of these. It's not 300 plus 5. The 5 means the entirety of the 2 years. And if I want to resell it because it's older, I get less money, 6,200. And I have this table for up to 6 years. And let's assume we currently have no car, but we must have a car at all times over a certain planning horizon. In this case, it's over the next 6 years. At which point, let's say we will get rid of the car, we'll sell it, and we'll have to move on to another city because perhaps we were relocated for another job. So the question becomes, when is it optimal to replace this car so that we minimize, right, the costs of owning, maintaining, and purchase over this horizon of 6 years? Now we can think of this as a shortest path in time, right? So I'm going to draw a picture here like I did for the previous network problems. The nodes are the locations. Where are we going to be, in quotes, locations? You can think of them as the beginning of each year. So the first node here is beginning of year 1. This is where I am now. And the years that matter to me are year 2, beginning of 2, beginning of 3, beginning of 4, 5, 6. And I'm going to go all the way to the end of year 6, right? Because this is a 6-year planning horizon, which matches beginning of year 7. So that's why I have a year 7 node here. And the path is, well, where I am now is year 1. So this is a supply of 1. This is me, one person. Where I want to go to, the destination node is year 7, so there's a demand of 1. They want me there. And then years in the middle are just pass-through points, so they have no supply or demand, which means their number next to them is a 0. They're just transshipment nodes. Now for the arcs or arrows in this picture, I have to think about what are the ways in which I could travel through this 6-year planning horizon, right? And I basically can do anything in the sense that as long as I'm going from a given year to a year in the future, right, it's possible. And you can think of the span of the arrow as representing how many years you chose to keep the car for. For example, the strategy that says keep the car for a year, sell, buy a new one, and do another year, and do another year, and keep doing like this. Every year you sell and buy and sell and buy, could be this path. I buy in year 1, keep it for a year, go to year 2, sell and buy another. Keep for a year, go to year 3, sell and buy another. So these are my 1-year jump arrows or hops, right? Another strategy is, well, why don't I do every 2 years? So I buy in year 1, I keep it all the way to year 3, replace the car, keep for another 2 years, replace the car, keep for another 2 years, and then finally sell it, right? So the 2-year hop is represented by an arrow that spans 2 years. And I could combine these things. I could do a 2 followed by a 2, followed by a 1, followed by a 1, right? Buy 1, keep for 2 years, replace. Keep for 2 years, replace. Then keep for 1 year, replace. Keep for 1 year, replace. And then you can see I could do like a 4-year hop, followed by a 2-year hop, followed by a 1-year hop. I could even dramatically just, I just buy it, stick with it the entire time. It's that big arrow here. Buy it in year 1, hold it for 6 years, then sell it. All of these are possible choices. And the idea of modeling is I should include in the model all the valid possibilities and let the solver crunch through the numbers and decide, well, this is the best one. So I have not drawn in this picture all the possible arrows it could have, but essentially any arrow that goes from any year to a year ahead of it, of being it a 1-hop or a 2-hop or a 3-hop, will exist, right? So for example, there are arrows departing from node 2 to 4, 2 to 5, 2 to 6, etc. Great. All right. So now that we have all the nodes with their supplies and the arcs, the only thing missing for this network picture to be complete and for us to do a solver model is, well, what are the costs involved, right? If this were a plain trip shortest path, the arcs could have on top of them their costs as, for example, mileage or time to traverse that route. In our case, let's think about it. For example, let's look at a 1-year hop here. What is the expense, right? If I do this, let's look at the table. I first buy the car for $10,000, right? Let me do this calculation here. So the 1-year hop, I buy the car for 10,000. And I will spend, according to the previous table, maintaining 300. When I get to the end of the year, I will sell the car, so I recoup 7,000, right? So it was 10,300 in expenses, and I recovered 7,000. So the net expense for a 1-year hop is $3,300. If I did a 2-year hop, right, I spend 10,000 to buy, plus, according to the expense table, $500 to maintain. And when I sell a 2-year-old car, I recoup 6,200. So the net expense, right, net expense of following a 2-year hop is 4,300. Now let me make a comment on this. Because in the data for this problem, we are ignoring price changes and inflation, right? Oh yeah, we're saying that the car always costs 10 grand. Well, maybe next year is going to be a little more, right? And we're saying that these costs are constant no matter what year you're in. Because we are making that assumption, a 1-year hop at any point in time, as in be it here or later, will always cost $3,300, right? Excuse me. So when I go and pick an arc that spans a single year, let's say from year 1 to year 2, or from year 2 to year 3 here in Excel, you see that they all cost $3,300. Right? Same is true for 2 years and 3 years. Any given amount of years you're keeping the car for will have the same cost. So every 2-year hop from 1 to 3 or 2 to 4 will be the same 4,300. And I could continue this calculation for a 3-year hop and a 4-year hop and a 5 and a 6. And that's where all the numbers here in this cost column D are coming from. They're coming from calculations like the one I just did here with you for you to see. Okay? So at this point, we have all the ingredients we need to model the problem in Solver and solve it. Now, if you're curious, well, what if I wanted to include inflation and price change? Well, that would be very simple. You just go here and change this calculation. If you're calculating the 1-year hop maybe from year 2 to year 3, and you think the car now costs more money, you just update this number or whatever, all the numbers that need to be updated in that particular calculation, and make this number here different from the hop from 1 to 2, right? So it's a simple change. So the only thing that you would have to change would be the values in this column here, but everything else would remain the same. Okay, and just for the sake of simplicity, we're just ignoring those changes. Great. So they want to know, minimize overall costs. How should I go through the course of 6 years while having a car at all times? How often and when should I replace it? The moment we transform this story into a network, with appropriate nodes and arcs and supplies and demands and costs on the arcs, we can pretty much take this story and throw it in the garbage, because all that matters now is that this is the network we want to model. So from this point forward, this is a shortest path problem. I am in city 1. I want to travel to city 7. These are the roads available, and these numbers in column D are the cost of traversing them. You could think of them as mileage or whatnot. And that's it. So as we did before, and if you don't recall this, you can go back and check the transshipment video or the shortest path video. We're going to do that inflow and outflow idea. So just to briefly show you the math for this, right? As usual, for a network problem, we create one variable for every arc or arrow in the picture. And we have been calling them xij, where the first number below x is the origin, where you're departing from, and the second number is the name of the destination node. So this x12 is the variable for the arrow or arc that goes from node 1 to node 2. Okay, don't confuse that with x12. If you prefer, you can put a comma x1, comma 2 there to differentiate. So notice that every x that represents a 1-year hop, 4, 5, 5, 6, 6, 7, costs 3,300. Every x that represents a 2-year hop costs 4,300, and so forth, all the way to the big long arrow that says, I'm just going to keep the car the whole time. Buy it once and be done with it, and that costs $12,600. Then, if you recall, every node of the network needs a constraint. The supply node here simply is going to say, I have to depart from node 1. So there's a supply of 1 in node 1, and this is just saying whatever departs node 1 from 1 to 2 or 1 to 3 or 1 to 4, etc., all the way to 1 to 7 should equal the supply, because supply matches demand. It's a 1 supply, 1 demand. For the demand node, we just have to say I have to arrive there, right, in the quantity of 1. So whatever enters, all the arrows that enter node 7 equal 1, saying get in there. And for every node in the middle, because they are just pass-through points, what I have to say is what goes in has to equal what goes out. So for example, node 2, there's only an in from node 1. And what goes out can be from 2 to every node in front of it, 2 to 3, 4, 5, 6, 7. Now, if you pick a node more in the middle, there are more ins, right? Node 4, I can get into it from nodes 1, 2, and 3. And I depart from node 4, I can go to 5, 6, 7. Okay? And that's what the math is. So in our modeling of these Excel problems that represent networks, we have been transforming these formulas all into an in minus out shape, which is what these middle 5 here are. This is representing the out of node 1. So as you recall from the previous videos, if I do in would be 0 minus out equal, because I minus the left hand side, I minus the right hand side, so that's why you have a -1 here. Great. So let's do that. We're going to calculate the in part of every node, right? Every node will have an in minus an out equal number. So everybody has the same pattern of formula. The in, the out, take the difference, equals number. So the inflow, and I'm just going to go through this formula more quickly now because we've seen it before. If you don't remember, click on the link below in the description of this video that takes you to the transshipment problem, and you'll see how that goes. So the inflow is a sum if. I check to see, because I want arrows that are coming into this node, I look at the destination column, saying, find me in this column here my name, or my name, I am node 1, my name is in F4. If you find my name, meaning you found an arrow that goes into me, then give me the corresponding x variable for that arc and add all of those, all of the x variables whose end point is me, and in this case me is I'm node 1, all of the arrows that end in node 1, add them in here. And then to do the out, well, arrows that depart from a node, I look at the departure column. Where are you departing from? Look here, anchor that, because you're going to copy this down to the other nodes, and say look in column B and look for the value 1. Whenever you found it, or you find it, it means you have found an arrow that departs from node 1. I want to, in that case, then go to column A and grab the corresponding x variable for that arrow and add all of those in here. So this will be adding in this cell H4 all x variables that depart from node 1, who in turn represent the outflow from node 1. And the in minus out is the difference, in minus out. So once you have all of these properly typed in and anchored, you can copy them to every node. And that produces all of these 7 formulas that we have in the math here. The final formula for us to create is the objective, right? But that is simply every x variable multiplied by its corresponding cost that we calculated in this fashion here. And to do that, we can simply use a sum product. Every x variable multiplied by its corresponding cost goes like that. Great, we are now ready to go into the solver and see the objective cell is the one we just wrote down, the G12. It's a minimize because it's a cost problem. The variables are my x variables from A4 through A24. And the constraints will be these 7 node constraints, right? The in minus out of everybody equals the number here on the right-hand side. Don't forget to make the variables non-negative and change this to the linear simplex solver, because this is a linear problem. And we can solve this now. Great. It's telling me that the cheapest way to have a car over the following 6 years, assuming that these are the maintenance and resale and the car costs 10 grand to buy, will cost you $12,500. So how do I do it? Let's take a look. I begin in node 1. It's telling me to go from node 1 to node 5, so that's a 4-year hop. And when I am in node 5, it's telling me to go to node 7, that's a 2-year hop. So it's telling me to go like this. Buy this car, new in year 1. Hold it for 4 years and end here in year 5. Sell it, buy another, hold it for 2 years, and then end in year 7, at which point you'll sell it and move on to your next job in another city. Okay, and this is the cheapest replacement strategy in this case. Now, just a final comment, because we are not introducing price changes over time, it means that this 4-year hop followed by a 2-year hop would cost the same if I reversed these and did a 2-year hop followed by a 4-year hop. All right? And that is a strategy that turned out to be the best one in this particular case. Okay? So this is it for this problem. Again, it is interesting to see that equipment replacement boils down to, right, just being a shortest path problem in disguise, and this is how you convert them and model them together this way. Okay, I hope this video was useful for you guys, and it was nice to have you back here. and I hope to see you again for more videos. Bye bye.